Hi, good evening, everyone. I'm really excited to be here and doing this talk, so let's just jump right in. This is Antarctica. This map is positioned over the South Pole, and you can see South America sort of to the west, Africa to the north, and Australia down in the bottom right corner. And I'd like to specifically get you guys to just pay attention to this opening between Antarctica and Australia because we're going to focus on it a bit later in the talk. So moving on. As some of you know, the Earth is made up of several plates. And these plates are all sitting on the mantle. These plates can be made up of oceanic crust, continental crust, or both. And they're all moving. Now, where plates touch each other, where they border each other, there's three kinds of boundaries. The first boundary is what we call a transform plate boundary. And that's kind of what we see in the San Andreas Fault in California. And that's when plates move relative to each other. So like that. The next type of boundary that we're going to be talking about is a divergent plate boundary. And that's when plates are moving apart from each other. And this is really important for my talk because this is what creates new ocean basins between continents when they separate. And the third type of plate boundary is what's called a convergent plate boundary, and that's when two plates move towards each other. And that's what we see in Japan nowadays. So just focus on the divergent plate boundary. It makes new ocean basins. So Tom already brought up this geological age, but I'd just really like to focus on it. We're going to be looking at around 230 million years ago until the present. And just a reminder, the age of the dinosaurs is the Mesozoic, the age of mammals is the Cenozoic, and us geologists use diagrams like these to break up geological time, which is really, really immense. If you can think about it, the Earth is 4.5 billion years old, roughly, so that's a huge amount of time. We use these to just really try and break down that huge time into smaller, more bite-sized chunks. So this is a map of distribution of rock types in the southern continents. And it's a bit complicated, so we're just going to take it piece by piece. But the really important thing that I want to draw your attention to is a layer of glacial tillites, and that's this type of rock right here. And you can find it in all these continents that are labeled. So Antarctica, South America, Africa, India, and Australia. So what a glacial tillite is, basically a sediment that was dropped off from a glacier. And glaciers pick up rocks and sand and stuff and just drop them as they move. But what I really want to draw your attention to is if all these continents were covered in ice in this shaded area in their present position, the Earth would be a giant snowball covered in ice. But if we look at rocks from the same age in the northern hemisphere, we see evidence of warm, lush climate. So we know that there can't have been glaciation this large in the Earth this time. So how are we going to reconcile this? Well, what does this mean? Well, basically what it means is all these continents were connected, as Tom was saying, in a supercontinent called Gondwana. And we have even more evidence of this. So before even the theory of plate tectonics came along to explain why the Earth's plates were moving, paleontologists have developed these fossil distribution maps. And the really important thing that I want to draw your attention to on this slide is this land reptile on the top right, and it's called Lystrosaurus. Shaded in brown, that's where you find him, so Africa, India, and Antarctica. And basically what this is also telling us is that Lystrosaurus was a land animal, like a cow. There's no way that it could swim between Antarctica and India. So pretty much the only way we can understand why Lystrosaurus is on all these continents is because they were joined together. Here's some fossil evidence of forest. So these are fossilized tree leaves that you find on Antarctica, and this is just showing that, you know, Antarctica, like Tom was saying, not always as cold as it is today. Cold Antarctica, definitely don't see any trees here. But the interesting thing is, if we look at the modern record, this is in Tasmania. You can actually go to Tasmania and find a really similar ecosystem in Tasmania as what was on Antarctica millions of years ago. So if you guys are interested in, you know, kind of going to Jurassic Park, going back in time, go to Tasmania. There's some really cool ancient ecosystems that are there just, you know, just doing their thing. And here's a really interesting, this is a really interesting spot that Claudia's been to. And all these trees in the foreground, these are all what we call nothofagus trees. And this is a really interesting tree because it has a really interesting distribution. And if we just look at, you know, a close-up of these trees, you know, pretty normal. But this, what we have here is a distribution map of nothofagus. And what I'd like to point out is that these are fossilized nothofagus and modern nothofagus. So we find fossils on Antarctica, and we find modern nothofagus trees on South America and Australia. But what's really important is that we don't find them on India and Africa. So if we know that all these continents were joined together at one time, why is there trees on Antarctica, on Australia, and South America, but not on India and Africa? Well, we can explain that by looking at a paleogeographic reconstruction. And this is basically a map of 100 million years ago put together by a huge project, huge team of geologists. And what we can see is that Africa and India have already separated from Gondwana. And the type of plate boundary that I was mentioning earlier, the divergent plate boundary, that was happening between Africa and Antarctica and between Africa and India. And that caused these plates to separate and a new ocean basin to open up in between them. So if we fast forward in time to 50 million years ago, we see that India's already jetted off up north, Africa's moved further away, and the opening between Australia and Antarctica is opened up. And this is important because it correlates with a slight cooling in Antarctica because Antarctica is surrounded by more ocean waters. But the really important thing is that Australia and South America are still connected here. So the Drake Passage, as we call it, hasn't opened up yet. Fast forward through time even more to 20 million years ago, and we see that South America and Antarctica have separated enough that we can open the Drake Passage and cause this Antarctic circumpolar current to form. And Jeremy is going to discuss the ramifications of that and how it affects the climate. But thanks for your time. Good evening.